to the Process Control Fundamentals training module. At the end of this module, you will be able to define process control, list the elements of a simple feedback loop, differentiate between open loop and closed loop control systems, and describe the difference between continuous controls and discrete controls. Process control simply refers to the control of a process. The main goal of process control is to stabilize process operations in order to consistently produce the desired results, and it can be automatic or manual. In modern processing and manufacturing industries, process control is frequently implemented by automated, computer-based control systems, which utilize a number of different tools. The fundamental building block of these systems is the process control loop. Discrete controls are also frequently included to automate sequences, functions, or tasks. In addition to stabilizing operations, control loops and discrete controls help prevent process upsets, injuries to personnel, and equipment damage. Process control loops are the basic building blocks of a process control system. Process control loops utilize various sensors, transmitters, control hardware and software, algorithms or calculations, and actuators or outputs to ensure that the process runs in a stable, predictable, and consistent manner. There are actually two types of control loops. One, open loops, which often require manual input. And two, closed loops, which can operate automatically or be converted to open loops by putting them in manual control. An open loop controller adjusts an input variable to produce the desired output without direct influence from the output variable. One example of an open loop controller is shown here. In this system, a steam coil is used to heat liquid in a tank. A manually adjusted valve on the steam line is used to affect the temperature of the liquid. In the best case scenario, the relationship between the valve setting and the liquid temperature is well known. However, because this is an open loop, a final measured liquid temperature is not used to change the valve setting. If this sort of feedback were used, this would be a closed loop controller. Open loop controllers are sometimes referred to as non-feedback controllers. They are best used on well-defined systems where the relationship between the input variables and output variables are known. If a temperature sensor were installed on the tank or outlet line, and the signal from the sensor was used by the control system to adjust the valve setting on the steam line, the controller would become a closed loop or feedback controller. In a closed loop control system, the input variable is adjusted based on the measured result or output. The basic elements of a feedback control loop are a process input variable, the valve setting on the steam line, a process output variable, the temperature of the liquid, and a controller, a device which compares the measured output variable to the desired result and calculates a new valve setting. The main advantage of closed loop or feedback controllers is that they are better able to react to process disturbances or variations. So, for example, if the incoming liquid temperature were to drop suddenly, the temperature sensor would detect the corresponding change in the outlet stream temperature. The controller would then calculate how much to open the valve to increase the steam flow and increase the temperature of the liquid. To better understand the difference between open loop and closed loop control, here are some examples. Open loop control examples include wash cycle and water temperature selection on a washing machine, These are both selected based on human judgment. The cleanliness of the clothes is not measured. Time settings on an automated lawn sprinkler system. The moisture content of the soil is not measured. Closed loop control examples include thermostatic control of room air temperature. The air temperature is continuously monitored, and the controller turns the furnace or air conditioner on and off to maintain the temperature at the desired setting. And cruise control on an automobile. The system monitors the car's speed and adjusts the gas flowing to the engine to maintain the speed at the desired setting. The temperature control of a liquid in a tank and cruise control on a car are all examples of continuous control systems. In these systems, the results or outputs are continuously monitored, and the controller continuously adjusts an input variable to maintain the desired results. Continuous control systems are commonly used to control flows, temperatures, concentrations, and other measurable results in continuous production processes, like those used to produce paper, plastics, chemicals, and fuels. Discrete controls are also often used in manufacturing industries. These controls monitor the state of an input variable and perform a discrete or digital action based on the value or state of the input variable. There are two types of discrete control: logic control and sequencing. Logic controls use sensors and switches to initiate actions. The robotic assembly of a car is a process that utilizes discrete logic controls. For example, the robot used to install the windshield on a car would first determine whether the new windshield was available and in its proper place. Then, it would determine whether the car was ready and in its proper position. When the robot has received signals indicating that both are ready, it would pick up the windshield and move it to its correct location on the car. Sequencing is a type of discrete control that works in an open-loop fashion. Sequencing systems use timers and counters to advance and move through a cycle. They are commonly found in household appliances, like washing machines and dishwashers. In industry, logic and sequencing controls are both typically implemented on programmable logic controllers, or PLCs. Elevators use a combination of logic control and sequencing. When you push the up button to summon an elevator, the control system causes the elevator to stop and open its doors when it reaches your floor while traveling upwards. The doors close behind you after a preset period of time, unless you break a safety light beam. Then, after the doors have closed and you have pushed the button for your desired floor, the elevator travels up to that floor, stopping at any floor along the way where an up button has been pushed. In this example, logic controls use the states of the buttons, inside and outside the elevator, to initiate actions. A sequencing control uses a timer or counter to hold the door open for a period of time. Interlocks and alarms are specialized controls that can be used in addition to continuous and discrete controls. They can prevent process upsets, injuries to personnel, and equipment damage. Interlocks. The safety light beam used to prevent the elevator doors from closing on you is one example of an interlock. When the light beam is broken, the elevator doors automatically open for a second time period. Another example is the lock on a self-cleaning oven door. The lock is interlocked to prevent the door from being opened until the oven temperature has dropped sufficiently. Alarms. If the safety light beam for the elevator door is broken too many times, or if a self-cleaning oven causes something to burn, an elevator alarm or smoke alarm will be activated. This initiates human intervention to figure out what is wrong. This module began with discussion on process control and the basic building block of process control systems, the process control loop. Both open-loop and closed-loop controllers were described. The difference between continuous and discrete controls was covered, followed by a discussion on the two main types of discrete controls, logic controls and sequencing. It is important to note that process control systems at large production facilities contain all types of controls, many of them hybridized to contain more than one type. This module should provide the basis for understanding control systems.